So today I'm going to talk a little bit about my PhD work and also my ongoing research on exploring formaldehyde and nitrogen dioxide variations with insights into surface ozone formation and some of the current challenges in air pollution that we're facing. So this video on this photo actually on the background shows smog over New York City on June 7th, 2023. And this is the day when the Canadian Wildfire Task Force has turned the sky orange, and that actually made to the headlines of many news in 2023. But in fact,
where is that?
it's New York City. The photo?
Yeah.
Yeah, I think it's New York City from the news. Sorry about the tech issue.
That's all right. Tenant on.
Actually, I can proceed this with this.
Yeah. Yeah. No. It was working.
Okay. However, air pollution is actually not a new problem here. Back in the 1960s, we also faced this smog issue over this region. And thanks to many efforts, especially made by EPA, leading by the Clean Air Act, we have improved air pollution significantly. However, as we see in the recent news from screenshots about news on 2022, 2023, and 2024, again, we're facing severe problems with air pollution. And today, I'm specifically going to focus on ozone, which is a major component of photochemical smog. But before I talk about some of my research, I would like to start with a background on what is ozone, why we should care about ozone, and what are the challenges we're facing. So this vertical profile shows ozone abundance in relationship to changes in altitude, and we're specifically looking at regions below 35 kilometers. Using the phrase credited by the US EPA, ozone in the stratosphere is called good up high because it absorbs UV radiation and protects life on Earth. However, for ozone near ground, we call it bad nearby because it is regarded as an air pollutant and it can damage and it poses many health concerns. Specifically, ozone exposure can lead to exacerbate respiratory diseases. This photo shows the healthy lungs, and with exposure to high ozone levels, it could narrow the lung pathways and leading to breathing difficulties. On the other hand, exposure to ozone can also damage plant tissues and hinder plant growth. Therefore, ozone is regulated as one of the 6 criteria pollutants. And this bar plot shows the number of people living in counties with air quality concentrations above the regulatory standards. And in 2017, as we see here, ozone kind of stands out as one of the problem child with millions of people living in places that have ozone levels above the standards. Specifically, today I'm going to focus on the Northeast US region. As this map shows, still have many places highlighted in blue that are designated as non-attainment regions. When you're talking about ozone, you might hear about MDA8 standing for maximum daily 8-hour average ozone, or 70 ppb a lot. This is because in 2015, the latest standards regulates ozone following those criteria. But why is ozone this challenging? This is mostly because ozone is a secondary pollutant, which means it's formed in the atmosphere instead of emitted directly. Specifically, ozone production sometimes is simplified using equations like this, mostly trying to highlight its precursor emissions with volatile organic compounds, VOCs, or carbon monoxide reacting with nitrogen oxides in the presence of sunlight. And as we go a little bit deeper into ozone production, this is actually a really simplified schematic for ozone production. But here I want to highlight the cycling between the HOX and NOx radicals that making ozone chemistry nonlinear, which means as we change the emissions of ozone precursors, you don't always get the same change in ozone. And specifically, if you reduce NOx, ozone could actually increase in some cases, which I will talk about a little bit later. On the other hand, both ozone and its precursors can be transported, so sometimes you can get high ozone events far downwind from the sources of its precursor emissions. But today I'm more focused on the nonlinear local chemistry part of ozone production. At the front and center of many people who are studying ozone, we really hope to more effectively reduce high ozone episodes. This is not only due to the regulatory purposes, but also trying to reduce the number of people who are exposed to high ozone levels. And to do that, we would like to better track and also understand the spatial and temporal variations of both ozone precursors and this production chemistry. So starting with the question of which precursors should we target, people, this is a figure adapted from the Daniel Jacob textbook. And specifically here, we have NOx emissions on the x-axis and VOC emissions on the y-axis. And the isoflex bars are showing ozone concentrations in parts per billion. And using figures like this and the ratio of VOC to NOx ratio, we hope to understand where we are on this region and therefore to predict what changes in ozone can we get if we change the ozone precursor emissions. So this transitional threshold values is often calculated using models or observations. Specifically, in the red region that we're looking at with high VOC to NOx ratio, implying NOx sensitive region, ozone concentrations would decrease with decreases in NOx, and changes VOC would have a less impact over here. However, with low VOC to NOx ratio, indicating a NOx saturated region, and this is the case, we're talking about ozone increase with reductions in NOx, and decrease with reductions in VOC. However, if we were sometime along this transitional line, changes in both VOC and NOx would lead to ozone changes. And looking back at this diagram that I showed earlier, it is very challenging to have a comprehensive measurement of VOCs at all times because it refers to a large group of species. So in this case, formaldehyde is often used as indicator for overall VOC reactivity because it is the intermediate product of many VOC oxidation. On the other hand, NO2 is the dominant form of NOx and is also measured continuously across many sites. And the benefits mostly of using formaldehyde and NO2 is because they're measured continuously, or not, but like we have available measurement of them. So looking back to this isoplot that I showed on the right, we're using formaldehyde as a proxy for VOC and NO2 as a proxy for NOx, and using the ratio of formaldehyde to NO2 instead as an indicator for the overall ozone formation chemistry. So if you're following with this, I added this icon showing the in situ monitors, meaning both formaldehyde and NO2 are measured on the ground. And this here, I highlights the active monitors for NO2 because NO2 is also regulated as one of the criteria pollutants. We have an extensive network and many efforts made to measure NO2. On the other hand, formaldehyde, well, it's designated as the hazardous air pollutant. It also measured, but across fewer places, but especially with many photochemical assessment monitoring stations. We also call them PEMS. I want to mention, as you see from here, that formaldehyde measurements are quite scarce. There are actually many state agencies making their own measurements, which are probably not available online. So I want to use this map to highlight the great efforts, but there are also observational gaps existing for the observation of both NO2 and formaldehyde. On the other hand, we also are growingly having the capacity to observe major trace gases from space. So these two plots basically highlights the efforts by NASA and ESA. Don't be intimidated by quite a lot of instruments that I showed on this figure. Here, I only want to highlight 3 instruments that are specifically designated and include the measurements or retrievals, as we see for formaldehyde and NO2. So GOM is the first one, was in operation from 1995 to 2011, having retrievals of formaldehyde and NO2. It has, to that date, it's like a breakthrough, but right now we think 40 by 320 might be too coarse. And it retrieves formaldehyde and NO2 every 3 days in the morning. And for the 2 more recent instruments that we have from OMI and TROPOMI, which are still in operation now, and we can see the improvement in the spatial resolution to TROPOMI to 5.5 by 3.5 kilometers. And both OMI and TROPOMI are what we call sun-synchronous. Aboard sun-synchronous satellites, which means they have retrieval once every day. And in the cases of OMI and TROPOMI, they're both at the early afternoon time, local time. However, for OMI and TROPOMI, we have global coverage, but it misses diurnal variations. And therefore, it's really exciting to enter what we call the GeoAQ era. So the geostationary satellites, they are able to retrieve those trace gases for their diurnal cycles during the daylight hours. However, those instruments have a limited field of regard. Specifically, they're only targeted at one specific region. And that's why we need this constellation of 3 different instruments that are currently in plan now. First one showing on the very left is TEMPO, which was launched in 2023 and is staring at North America region. And in the middle is a Sentinel-4 overseeing Europe, according to the latest news that I find published on February 20th. It's supposed to be launched soon in summer 2025. And also GEMS showing on the very right side. It was launched in 2020 and seeing the Asian Pacific region. So we should be able to have this constellation ready to look at a lot of new problems now. We're solving new challenges in new ways. However, although I talk a lot about the satellite instruments, well, what they actually measure are the backscattered solar radiation, not the actual atmospheric composition. This means we call them retrieval because they are not the actual measurements of the concentrations. And we need to rely on the knowledge of the spectroscopic signatures of different species. And we often require this a priori first gases information, normally from models for the initial state of the atmosphere, but also relying on that to determine the vertical distribution of the trace gases. Although this is posing a lot of data set that we're able to explore, we have to keep in mind that there are also a lot of uncertainties, errors, and sometimes model biases carried over as we're doing those retrievals. So coming back at this, so now we are able to combine both remote sensed information as well as the in situ monitors. And coming back to this from question that I posted earlier in this presentation. Specifically, today I'm going to talk about 2 kind of sub-questions underneath it. First, we hope to understand how formaldehyde, NO2, and local ozone production photochemistry are different. Here, I want to composite over the highest ozone days versus the other days and want to study how they vary diurnally as well as seasonally. And secondly, even though we have this information from space, as I talk about, what we actually care about is more near surface for many health concerns. So, and in order to make the troposphere vertical column density retrievals more readily applied to some problems that we're caring about, we need to understand how those changes are related to what's actually going on the ground. Starting with the first project I hope to share today. So this one, I did more like a composite view on the highest ozone days versus other days, mostly relying on remote sensed instruments, but also combined with some in situ measurement. And this work is made possible by the Long Island Sound tropospheric ozone study. We call it LISTOS. And I just realized this exactly looks like that map hanging over on the wall. So it's kind of good to show the study in this group. And LISTOS, with the goal to understand ozone problem in the New York City and Long Island Sound region, had extensive planning of different measurements. So we were able to look at a lot of problems in more details. But start with this, I kind of sorted out the highest ozone days in May to August for the year of 2018. This is when the LISTOS took place. And in this case, I'm showing the calendars in 2018 from May to August. And I sorted out the high ozone days using the survey measurements. So this is defined as having MD8 ozone exceeding 70 ppb at any of the surface monitor within the LISTOS region that I showed in the previous slide. In those days, it's probably not obvious there, but I marked them beige. But that's okay, because what we actually use are those days showed in orange, and those are the days when we have retrievals available from TropoMe. Another issue with using satellite measurements is that you are oftentimes limited by data availability. If you have cloud cover, you probably are not able to retrieve the best quality, and you probably are not advised to using those data points. So this leaves us with 19 out of 22 high ozone days for the summer of 2018. And I regrid those level 2 data to a resolution of 0.05 by 0.5 degrees. And then I try to match the same number of mid to low ozone days, what I also call other days, for comparison. And I specifically choose the same day of the week to try to minimize the impact of weekend to weekday-weekend impact. And those days are marked in blue. And we're fortunate to also have the aircraft retrievals from Geotasso and GCAS. Both of those are more like the test beds for instruments like Tempo, and they have super high resolution. I use their it's originally in 250 meters, and I use the processed R1 data regrid to a resolution of 0.01 by 0.1, and this is much higher than TropoMe already. And we have 10 days. The bad side about aircraft measurements is that you're not available to have them every single day. So for this case, I selected 10 days marked by slash. So this is 5 high ozone versus 5 mid to low days. And for the interpretation of the formaldehyde to NO2 ratio for this study, I'm following up at Xiaomeng Jin's study. In her 2020 paper, she used multi-satellite formaldehyde to NO2 records from 1996 to 2016 over 7 major US cities, including New York City. And in her study, she calculated the threshold values based on the observed ozone exceedance probability for those 3 photochemical regions that we defined earlier. However, the satellite retrieve formaldehyde to NO2 ratio is still a really controversial topic here. It's kind of really handy because for a lot of the air managers, you're able to have formaldehyde and NO2, and look at how simple it is. You just take the ratio. But of course, not only to mention that the formaldehyde to NO2 ratio, the retrievals themselves could have some bias, but also the threshold value definition is very hard to be consistent. But in my study, or in this case, I more want to use the ratio as the indicator of the transition in photochemical regions on the highest ozone days versus other days. So a lot of caveats, but let's start to look at some of the results. The first figure is showing formaldehyde densities On the right side, I'm showing the average. The right column is showing the average on 5 high ozone days in comparison to the left side showing formaldehyde densities on the mid to low ozone days. I take out the pixels over water. As you can see, those are marked in gray because there are some artificial issues with formaldehyde retrievals over water. And for the top row is showing geotassel GCAS retrievals at 0.01 resolution, with the middle row also showing geotassel and GCAS, but regraded to the same resolution as tropomi showing on the bottom. This is basically trying to say if the difference we see between those two are actually due to resolution. But in this case, for both geotassel GCAS and tropomi, we find an increase in formaldehyde densities on the highest ozone days. And we look at ozone, and this is across the entire domain. However, for NO2, we also find this increase in NO2 column densities, but this is more concentrated to over the urban core, but metropolitan area. And next, we take the ratio of formaldehyde to NO2. So for this map I'm showing here, the color bars is following what Xiaomeng calculated. And the site, because the changes in formaldehyde is more substantial, which see the changes in formaldehyde levels more dominant than changes in the overall ratio. And for this, the colors towards the more darker blue side, indicating more NOx saturated production regime, whereas the colors towards brown and white, suggesting more NOx sensitive region. And for here, when we're comparing the high ozone days versus the other days, we see the New York core center remains in a NOx saturated region, whereas the nearby regions are shifted towards higher ratio values, indicating greater sensitivity to NOx. On the other hand, if we compare tropomi with geotassel and GCAS, tropomi in general suggests greater sensitivity to NOx. And we extend this analysis for the 19 versus 19-day comparison using tropomi, which is suggesting the same trend of increasing formaldehyde, NO2, and the ratio values on the highest ozone days. However, so far, I've only included the remote sense retrievals, but I'm also trying to see if these changes are also consistent with some of the surface or in situ monitors. Here, specifically, I'm showing the results from Pandora spectrometers. So the Pandora spectrometers are in situ monitors that are able to retrieve the column densities of NO2. And I'm showing the difference in the summer mean at different sites spanning across this transect of New York City. And it is also suggesting increasing NO2 column densities. On the other hand, I also look at emission cases and meteorology, and I find the meteorology result a little bit interesting over here. So the maps you're seeing here have the temperature averaged for 19 high ozone versus other days in the background, and the vectors you're looking at showing wind vectors with speed and direction. Normally, if we're thinking about high ozone events, it's coupled with high temperature and air stagnation because it allows air pollution to accumulate. However, in the case of New York City for this year, we're seeing more than 2/3 of the high ozone days are associating with faster southwesterly winds, suggesting a possible impact of transport. Okay, as a little bit summary of the first project, we do see both satellite and airborne sensors implying enhanced sensitivity of local ozone production to NOx emissions on the highest ozone days. And this is suggesting that additional NOx emissions control may reduce ozone levels, especially on the most polluted days. However, because we're relying so much on tropomi, we're not actually talking about anything related to diurnal changes in this case. However, as I mentioned earlier with the launch of Tempo, we hope to draw new insights from formaldehyde and NO2 variations, and hope to understand the hourly variations in both the column and surface and trying to relate them. And that's why for the second work I'm talking about today, I hope to characterize the diurnal variations in both ground-based surface measurements as well as column retrievals at these 7 sites, which spans an upwind New York City at Rutgers, and also including these 3 sites closer to the urban core, as well as the sites downwind. This table on so for this study, I'm mostly using in situ observations. And this table on the left side is showing availability of different trace gas species at each site. And I'm using NOx, CO, and ozone measurements from the state and local air monitoring stations. For formaldehyde, we do have it measured at Westport for 2018. But because we only have that one site, and I hope to include more data for formaldehyde, I'm also using the formaldehyde measurements available through the New York State Department of Environmental Conservation and New York Botanic Garden and Flux Fund from 2020 and 2021. In addition, all those 7 sites have Pandoras co-located, and I'm using their NO2 retrievals. For 2018, unfortunately, there was an issue with outgassing associating with formaldehyde retrievals, so I'm not including those in this talk or my research for now. Because of the scarcity of data set that I mentioned earlier from observations, I'm also including this high resolution model simulation from WRF CMAC. This is at 1.33 kilometers. The video is showing the evolution of surface ozone on one particular day to demonstrate mostly the domain and the resolution of the simulations. And I'm using the trace gas species saved from the model and also calculated the vertical column densities of formaldehyde and NO2. I have to mention I also did a more rigorous comparison and model evaluation for WRF CMAC. You're interested, but I'm not going to talk about it right now. What's interesting about this transect, as we talked earlier, you do have different photochemical regimes here. Besides what we use from formaldehyde to NO2 ratio or other indicators, the state managers would also like to use the ozone weekend effect, which basically refers to the phenomenon that on the weekends, even though you have a reduction in NOx emissions, sometimes you can have higher ozone levels. And this occurs especially over some metropolitan regions where ozone production is super NOx saturated. And for this case, I'm showing the surface ozone concentrations averaged over the entire summer in the thick line. So this is colored by different sites. And the average on the weekdays, selecting Tuesday and Thursdays, are highlighted by triangles. And the weekend days, selecting Saturday and Sundays, are highlighted by the wrong side circle. So for Queens College, we do see the weekend ozone is higher, implying NOx saturated region. However, at Westport, we see a decrease, indicating more NOx sensitive region. And it basically mostly aligns with the spatial gradient that we found earlier. However, New Haven surface NO2 surface concentrations is an interesting case. It's not showing any differences at all. And we're going to talk a little bit why later. So first, starting to look at surface NO2, I'm selecting those 3 sites that I chose, like more representative sites earlier. So this is still colored the same way. And we're now looking at the DO cycle of NO2 concentrations for average for the summer at those 3 sites. And for actually 6 out of the 7 sites on this map, we find this 5-module peak of high NO2 concentrations occurring before sunrise and also later in the evening. And this reflects influences mostly on the anthropogenic emissions and photochemistry, as well as the boundary layer dynamics. However, if you note that we have the 3rd local maximum for NO2 at New Haven, this is most because this site is located at the intersection of 3 major highways, and there's a high local effect of traffic emissions, which we find high CO and NO concentrations at that site as well. On top of the surface concentrations in the color lines, I'm adding the column observations from Pandora, and the Pandora is showing as the black line average for the summer. And on top of that, I'm also showing the tropical mean retrievals, as you see, it's 1 time every day. And the mean is showing as a dot, and both the arrow bars and the shading is showing, the shading is not obvious here, but showing the 1 standard deviation. Drawing your eyes first to the New Haven side, the column density is actually not suggesting this high concentration in the noontime, suggesting this is probably more localized. And also, although New Haven surface concentrations are about the same magnitude as Queens College, the column densities is much higher. This is also suggesting another discrepancy of measurements at the surface versus the column densities. However, if we're looking at Queens College and Westport, the column densities changes mostly mirror those at the surface, and you could probably also note this kind of a little delay in the peaking time occurring at the column around 9 to 10 a.m. In comparison to the peak that we find at the surface. And this is showing Queens College as an example. I'm pulling out the NO emissions in the black line, as well as the planetary boundary layer height in gray here. In the morning before sunrise, where the planetary boundary layer height is still super low, we have this accumulation of NO emissions going in and have the surface air pollutants builds up. But as the planetary boundary layer height rises, it dilutes the surface NO2, whereas the column density still rise with increased morning time emissions. And this delay is not something new and also noted in other studies. Next, we kind of shift gears a little bit into formaldehyde, and I'm showing 3 different sites, just to note, now including Westport, New York Botanic Garden, and Black's Pond. For 2018, we have the Westport site showing in blue here, and to differentiate the measurements taken in different years, I'm showing 2020 in dashed lines and 2021 in the dotted lines here. So this is still the DO cycle formaldehyde. And formaldehyde, we do see this the single daily peak occurring in noon to early afternoon time, and this is because formaldehyde concentrations of those at those sites is more dominated by biogenic sources. We do note a little bit delay in the peak time that occurs in Westport compared to other sites. And this is kind of also consistent over the summer and associated with the lake breeze impact over the Long Island Sound region. It's kind of interesting also to note this interannual variability at New York Botanic Garden. So the difference between the dashed and dotted blue lines are much smaller than the differences if you compare that to the other sites. However, this is just their limited data set, but I think the interannual variability versus a cross-site variability is also something interesting. And then looking at formaldehyde, because we don't have the formaldehyde retrievals available, but we hope also to have some ideas and picture what we would get by the time we have instruments like tempo going up. And for this plots, I'm showing observed surface concentrations in the same color. And the model surface concentration is a brighter blue color with the black line now showing the modeled column. And we also find this interesting delay in when the peak occurs by the modeled formaldehyde. And for this case, triple me showing here because of this delay is missing the daily peak column densities of formaldehyde. And besides that, when we compare the observed surface concentrations to the model surface concentrations, we see Worf CMAC underestimate it a lot by 65% for the summer mean. And this is probably associating with the underestimation of isoprene emissions noted in BICE, but also generally across the biogenic emissions inventory in the New York City region, or the larger, broader region of New York. I would like to revisit this kind of comparison with Pandora retrievals available in recent years if they become validated. And then as a summary for the second project I'm sharing today, we do find the column retrievals show a delay relative to the surface measurements for the morning NO2 peak and midday formaldehyde concentrations. And we note that the current once per day satellite retrievals is almost peaking the daily minimum for NO2 and also misses the daily maximum for formaldehyde concentrations. And I find it's interesting to revisit a lot of studies that we do with tropomi that relies on this once per day retrieval in the early afternoon, and what are some new insights we would have if we introduce this diurnal variability, or looking at retrievals from different hours of the day for different applications like inversion models for emissions. So I'm going to right now talk a little bit about my ongoing work using Tempo. So this video is showing NO2 column densities on one single day on May 24th, 2024. And this is a day that there are many high ozone alerts over the Northeast state regions. And the left side is our old friend tropomi. It's static and remain at 1:30 p.m. local time. And on the right side is tropomi that we see varying concentrations of NO2 throughout the daytime. And for this case, I'm using the level 3 provisionary data at 0.02 horizontal resolution. And for both tropomi and tempo, I'm applying data filtering based on the recommendations. And with this variant observations from space, we're able to look more into the diurnal and seasonal variability. However, we're already able to see these seasonal variations with tropomi. So first, I'm showing the monthly mean from April to July from tropomi column densities of formaldehyde. And we see a clear seasonal increase in formaldehyde early column densities from April to July, as we expect to see from more biogenic impact. And the regional mean almost tripled for formaldehyde in this Northeast region. And then if we put tempo together with tropomi, the tempo is providing more hours than what I selected here, but we are still having some issues with earlier and later retrievals. Those are some news angles that we're observing we're using for the first time. So there are still a lot of ongoing efforts for tempo validation. But here I'm selecting 9:30 a.m., 1:30 p.m., close to tropomi overcast time, and then 3:30 and 5:30 p.m. in the afternoon. Here, each small pixel is showing the average of tempo data for for scans with start time plus or minus 30 minutes surrounding the labeled time. And right now with tempo, you're not only able to see the seasonal changes as you go from top to the bottom of each column, you're able to also see the diurnal changes as you go from left to the right on each row. Generally, tempo also shows this increasing formaldehyde column densities. And in the springtime, you're more able to see the signatures from anthropogenic emissions, whereas if you hit June and July, you see the dominance of biogenic emissions picking up. And diurnally, it also kind of aligns with our, I phrase as pre-tempo study, that formaldehyde tends to be lower in the morning and increase with higher in the afternoon, especially the 3:30 column. We're also looking at NO2 column density the same way. The tropomi is showing a seasonal decline in NO2 column density, in this case, from April to July. This is mostly associating with the lifetime of NO2 and photochemistry. And this decrease is more significant over the urban core regions. And if we're looking at the I hope you can see the black box, very small, over the New York region. We see a regional decrease of 32%. And looking at tropomi and tempo the same way as we did for formaldehyde, we find that diurnally tempo generally observes higher NO2 column density. This is the time we're talking about this delay occurring in the peak time for the column. And we are able to see that right now with the tempo. And we see a more daily minimum near the tropomi overpass time. However, NO2 is showing more complex changes as in terms of seasonal variations. If you're looking at different columns over here, and we're still trying to understand why. And since we have formaldehyde and NO2, I also take the ratio in this case, and this is using this the color bar similar to what we had earlier, but right now more as a trend of how the ratio values are changing. And more as what we would find that we see more NOx-saturated ozone production earlier in the ozone season than the midsummer events. And we also find more NOx-saturated region earlier in the morning compared to afternoon time. And the early morning time is more relevant for applications like traffic hours. And if we compare tropomi with tempo, we find tropomi indicates a more NOx-saturated ozone production regime with lower ratio values. However, as we're talking about, I added a question mark over there because this is not a really good comparison, but I'm just showing some initial results. I'm also doing a more rigorous comparison of tempo and tropomi by using the same a priori. So like I basically recalculated tropomi using the same a priori as tempo. And if you're interested, we could talk more about that offline. But so far, as a preliminary takeaway from this, we do find the formaldehyde to NO2 ratio indicating more NOx-saturated regime in the springtime compared to midsummer, and morning time compared to the afternoon, and putting it back in this key takeaway table over here. Before I close, since we talk a lot about satellite applications of formaldehyde and NO2, I also put up a table in my thesis, thanks to a lot of collaborators of specifically focusing on the retrievals of NO2 and formaldehyde, showing tempo, tropomi, but also trying to be comprehensive, including other instruments. And that is available through HayCast website, and it's a clickable table, and you can see the references and learn more about the details. And if you're interested, you can talk to me or scan a QR code over there. And lastly, I would like to thank the support for funding from NASA HayCast. I would also like to thank all my co-authors and collaborators. As you see, a lot of my studies are heavily dependent on data collection, and there's significant efforts made by people who are out there in the field and collecting data and making this study possible. And I really want to thank them for their efforts. And I want to thank you for your attention and staying with me in this room for the last 15 minutes. And I put my contact over there if you're happy to get in touch. Thank you.
Thank you so much, Dr. Tao. Do we have any questions here?
Student should always go first, but I'll go. We'll see what happens.
Okay.
So it's Tao Ma.
Yes,
That what
yes.
you go by? Enjoyed your talk. So since we've been studying these processes for 75 years or so, we're really in a place where what matters, I think, is how air quality managers can make good decisions about anything they can do to minimize ozone and exposure of humans to ozone. So they've been using these ECMA diagrams for all this time, VOCs versus NOx, and in your case, formaldehyde versus NOx. ozone typically peaks when it's warm out, and so on this axis, you have no control whatsoever, right? It's all, the formaldehyde is all coming from isoprene mostly, and the VOCs are mostly isoprene. And this axis, you have control over the emissions. And where what you'd like to know is where in that complex diagram you are going to be as a function of meteorology, so that you can predict sensitivity to NOx control, right? So there's temperature, wind speed, wind direction, source region, boundary layer height, right? Okay, so when it's warmer out, you move up this axis exponentially, right? And it becomes much more NOx sensitive. So where you are depends a lot on temperature, I think. Have you looked at from the models how the sensitivity D-ozone, D-NOx changes with temperature? Is that a useful variable for air quality managers to know how sensitive will the atmosphere be on a particular day with a particular temperature, maybe boundary layer height? How sensitive will ozone be to NOx reduction versus those variables? I mean, it's all academic until we start trying to control emissions and control ozone. So tell us what you know about the sensitivity as a function of temperature.
Okay, so for those who are online, we got a question from the audience asking about the sensitivity of ozone production or ozone control in terms of changes in meteorology. That's actually a really good question. There's although I haven't gone too depth in my work, but meteorology definitely plays a really key part in terms of both, because ozone production is a photochemistry, and so it improves ozone production efficiency on its own way, but also it enhances the production of things that are ozone precursors, as you talked about. Definitely, meteorology is playing a huge role in terms of how we're hoping to regulate ozone, especially under things like a warming climate. For this case, I'm looking at more like the urban places, and we figure out using diagrams like the VOC and NOx to figure out which region we're at, basically hoping to have some more control over what we can do. There's a growing discussion on the anthropogenic emissions part of VOC, and there's a lot of work going on in terms of the contributions of biogenic VOC, which we cannot control, versus the anthropogenic VOC leading by VCPs, volatile chemical products. And there's still an active research area on that field regard. And to my understanding, if we want to have some more control on the VOC side, it's good to have an idea of how much different sources are contributing to the ozone budget. And in terms of high temperature, sure, I feel like it's a complex issue as you're talking about. With temperature, you could also have a rising boundary layer, and you have to understand the transport, like where the winds are coming from. Because if you're thinking about your local region as one box over here, and then you have your local chemistry going on with the meteorology, like a boundary layer, like vertical intrusion. But you also have something that comes into your box via transport. And depending on where the wind are flowing and which air parcels you got, you could also have a very different way. And in terms of air quality control, definitely we face more challenges if you get extreme weather impact by like heat and wildfire transport, and that's some new challenges that I mentioned earlier in my talk with those head news. Those are actually more impacted by transport than like local production, where you have this orange sky over the city. And I think those are all some active research areas that we could look more into in the future.
I'm curious if in the realm of VOC production in cities, if there's a significant amount of biogenic VOC emission from like green spaces or green roofs, and is that something that like city planners take into account when they want to limit ozone? Like I know, like we have Central Park in New York City, and if that is a sizable contributor to ozone production through its emission of VOCs.
Yeah, I really like that question, because that almost feel like we're arguing for less trees to
Yeah.
reduce ozone, which we don't want. But actually, different species of plants, they have different emissions. And to my understanding of trees emit more VOC than other trees. However, this is not an argument for less oak trees planting, because we're not only care about air pollution, we also care about biodiversity in different places. I got a really interesting question during my defense, like if you have a 1 million tree plant in New York City, how do you distribute different plant species in order to avoid ozone? That's actually a really hard question because it's just like really hard to think about that. But generally, I think a better understanding of where the sources of VOCs are coming from and how much they actually contribute to productions like other VOC species and ozone, it's something you have to do first. You do have to have a good inventory to start to think about questions like that. As I mentioned, for the worst simulations, we have a low underestimation in formaldehyde, and that's generally true across many models, mostly because we don't have good emissions inventory. And as long as we don't have that, it's hard to do other things like plannings. Thank you.
Any other questions?
One
Yeah,
more. So I was intrigued by the plot of NO2 as measured from the ground, peaking earlier in the day as compared to the satellite data, which peaked later in the day. That sounds very much to me like a vertical mixing problem, that the morning emissions and production are mixing upward. Do you have any sense of how well the model is treating vertical mixing? Like from those aircraft campaigns, there's data on atmospheric turbulence as a function of time and space, and there's an opportunity there to compare how well the model is simulating turbulence versus reality.
Sure, that's a good question because so far I only talk about the total column density, so you get a sum of wherever you're looking at. But next step I'm planning to do is looking at vertical profiles, because only that you figure out where the high concentrations are, and I'm hoping to looking more into that in the future on the vertical profiles of NO2, formaldehyde, and ozone. Thank you.
Go ahead.
My question is, like, at the beginning of the talk, you take HCHO as the proxy of the VOC. So I'm wondering if other VOCs like peroxide will like compete with it to form ozone.
Yeah, that's another uncertainty of using formaldehyde as a proxy for VOC reactivity. But because I think motivation is more like we have data of formaldehyde the most, especially from space. So we hope to make good use of the data. But what you mentioned is definitely another source of uncertainties of, I think the question is how reliant or the uncertainties of using formaldehyde as a proxy for VOC reactivity.
Do we have any questions online? Oh, I mean, I actually have a question here.
So we have you see that already?
Can you see that?
Yeah. There are a couple of sources of differences between people and Omi. So one being that they have different sensitivity to different layers because there are different onboard different instruments. Another source of uncertainty, as I talk about, are the a priori information. So Tempo is using GeoCF model simulations as its a priori, and TropoMe is using TM5, and they have different both vertical and horizontal resolutions, and they're totally different simulations. So you could get different assumptions for the a priori information that could also lead to differences. The time when I recalculated TropoMe using GeoCF as its a priori, I do see the spatial differences changing a little bit, and that could partially explain why we do see the difference. But it's hard until you do those different testing, you could figure out where is the source of these differences. And also, I have to mention it's not a perfect match in time, although I labeled them both at 1:30 p.m. Because there's a little bit difference of timing when the scan is actually taking place over the same pixel. So even though I'm using a careful match of pixel by pixel kind of approach, I cannot promise they're like actually overlap exactly in time and space. And we see that NO2 can be transported a little bit, and yeah, could be seeing a little bit differences because of time offset as well. Thanks for the question.
Thank you. Do we have any other questions? Are we good? All right, it's time for lunch. Thank you so much, Dr. Tao. I'll see you guys at the pizza room. All right. Thank you.